All right, in this video, we're going to go over a couple of examples from the handout on centroids and moments of inertia. This is a homework handout. And our first one is going to be a rectangle with a circle cut out of it. What we want to do, the instructions say, find the moment of inertia about a horizontal axis through the centroid of the cross-section. Centroids and moments of inertia are used in beam problems, beam deflections, and beam stresses. The equations we're going to end up using are, to find the y bar, we're going to use the summation of each individual piece's y bar multiplied by its area divided by the total area. This may be something that you've done in statics at a previous time. And then for the moment of inertia of a horizontal line that goes through the centroid, we're going to calculate the moment of inertia I as the summation of the moments of inertia of each piece of a composite region plus the area of each piece in the distance d, where d is the distance between the centroid of the composite section and the centroid of that particular piece. And we're going to do the summation over however many pieces we have. All right, so that sounds kind of confusing at first, but let's kind of break it down and take a look at this specific problem, and then we'll look at the other two that are on the handout as well and calculate both their y bars and their moments of inertia. So if we look at this object, this is 7 centimeters tall, but it has a cutout, a hole up here. And if it didn't have a hole, we would expect the centroid to be located at 3.5 centimeters from the bottom. I'm going to use the bottom as a reference line. But because this hole is cut out, I would expect that the centroid would be a little bit lower than 7.5. So wherever it is, maybe it's about here. I'll tell you what, let's use a special symbol for the centroid. It's usually a circle with a couple quadrants filled in. So the first thing we need to do is we need to find the location of that centroid. It's going to be using this formula right here. I'm going to break this object up into two pieces. One object is going to be the rectangle, and it has its own centroid right there. And the second object is going to be a hole whose centroid is located at 5 centimeters from the reference line. So I need that 5 centimeter dimension, and I need to know that this distance is 3.5 centimeters. And the centroid of the rectangle is in the geometric middle of the rectangle. All right, so let me switch back to blue. My y bar with reference to my bottom of the bar where my reference line is located. You can put your reference anywhere you want. Out of habit, I just like the bottom. So I'm going to add together the y bar for the rectangle times the area of the solid rectangle, which is 7 by 4 centimeters. Okay, so the units on this term are centimeters cubed. Now, because that hole is, because that circle is a hole, we're going to take away the y bar A for that hole. Now, the y bar location to the centroid of that hole is 5 centimeters. What I mean by that, it's the distance from the reference line to the centroid of the circle. Okay, 5 centimeters is given in the figure. And then the area of the hole. Now, it has a radius of 1 centimeter. So let's use the form for the area of a circle of pi r squared. Right. So all that goes on the top, and then on the bottom goes the total area. So I'm going to take the area of the square as if it were solid, and then I'm going to take away the area of the hole. All right, I have my calculator handy. Let me just see what that number is. It's not something I can calculate off the top of my head. If I did my calculations right, I got 3.31 centimeters. And what that means is the distance from the reference line to the centroid of the composite region is 3.31 centimeters. Next thing I need is the moment of inertia of this shape about this horizontal line that goes to the centroid, this blue line that I have sketched in here. So I'm going to do that in the same sort of way. I'm going to find the moment of inertia of a rectangle about its own centroid, and I need to use the parallel axis theorem to transfer that to the horizontal line for the composite section's centroid. Okay. Let's go back and let's use this green color to highlight some of this. So here's the axis that goes through the centroid of the rectangle. I'll put this in green. The moment of inertia of a rectangle about its own centroid is 1/12 the base times the height cubed. Now, if you don't know that, on my website, I have this. It's often seen on back covers of books, but here's the moment of inertia of a rectangle about its horizontal axis. Here's the moment of inertia of a circle, and here's the moment of inertia of a triangle. I will give you this page on your exam 2, 3, and final exam. And down at the bottom is the parallel axis theorem. All right, so what we found now with 1/12 the base times the height cubed is about this green centroidal line for just the rectangle. But now we have to move that to the line down below, the blue line. So we're going to add in a area times the distance between the axes squared. The distance between the axes is 3.5 minus 3.31 squared. Now let's change over to red. Now I need to deal with the circle. Because that hole is treated like a negative area, I need to find the moment of inertia of a circle. Okay, for a circle, it's pi over 64 diameter to the 4th power. That's the way I remember it. So let me go pi over 64 2 to the 4th power. And then I also have the area of the circle, pi r squared, times the distance between the centroid of the circle and the centroid of the entire piece squared. So in this case, it would be 5 minus 3.31 quantity squared. And because we're taking this away, because it's a hollow portion, I'm going to put a big minus sign in front of that entire term. Let me come up with that number here for that value. All right, and so after putting those numbers in, I got 105.6 centimeters to the 4th power. Our moment of inertia term will have units of length to the 4th power. All right, let's take a look at the next one. And in this next one, we have a trapezoid-shaped cross-section. And the hint says treat the area as a rectangle and 2 triangles. Now, there are a couple ways to do this. One, you can make a large rectangle and have 2 take-away triangles. Or the way that I'm going to do it is I'm going to make this a central rectangle, and I'll have 2 solid triangles I'll add to it. Well, the first thing we need to do is find our y-bar location. And as we said before, let's go ahead and write down the formula again. Summation of the y-bar I a sub I that multiplied together divided by the total area. Okay, so for my central rectangle, this part right here, I'm going to have the area of 5 by 7. And the y-bar location for that rectangle is going to be 3.5, using my base as my reference line. I'm going to have 2 triangles, so I'm going to put the number 2 right here. And each triangle has an area of 1/2 the base. Okay, well, the entire distance from here to here is 5, and the total distance is 9. I have 2 on this side and 2 on this side. So 1/2 the base times the height. And the y-bar location from the reference line for one of the triangles is going to be 1/3 from the large end of the triangle. The y-bar location is going to be 7 divided by 3. Again, this number 2 takes care of both of those triangles. And on the bottom, I'm going to have the total area, 5 by 7, and 2, 1/2 the base times the height terms. All right, let's see what I get for my y-bar in this case. And by calculating those numbers, I got 3.167 centimeters. Okay, so what that means, I'll put this in red, is that the centroid of the entire cross-section is a little bit lower than the centroid of just that central rectangle. Centroid of the entire cross-section is located here. I'm drawing it in red. And that distance from my reference line is 3.167 centimeters. So now we want the moment of inertia of that shape about that red line that goes through the centroid of the cross-section. Okay, we're going to use the parallel axis theorem for this. We're going to break it up into those same 3 pieces. We're going to apply the formula summation of I for each piece's centroid, I sub ci, plus the area of each piece, the distance squared between the centroid of that piece and the centroid of the entire cross-section. We're going to add them up. In this case, we're going to use 3 different pieces. So let's do that down here. The central rectangle has a moment of inertia of 1/12 the base times the height cubed. But now we need to transfer it from its own centroid to the centroid of the cross-section. We're going to multiply it by the area, 5 by 7, and then the distance of 3.5 minus 3.167 squared. All right. Each triangle is going to be identical, so I'm just going to put a big old 2 right here. I'm going to multiply it by this term in the brackets. The moment of inertia of a triangle about its own centroid is bh cubed over 36, where b is the base. Now we got 7, so this way 7 cubed over 36. And then we need to transfer the moment of inertia about its own centroid to the moment of inertia entire cross-section. So here we're going to have the difference between 3.167 and 7/3 squared. That's the distance squared. Tell you what, let's move that over and make a little space. Should have put the area first. There we go. The area first would be 1/2 the base times the height. And then this is the distance squared term. Now 7/3 that's 2.33. Okay. And if I put all those numbers together, make sure everything's looking good here, we're going to get 194.6 centimeters to the 4th. 194.6 centimeters to the 4th. All right, and that is our result for that particular shape. All right, now let's take a look at the T-beam. All right, and in this problem, we have the dimensions that are given there. And we're going to break this up into 2 rectangles. Again, the first thing we want to do is we want to find the location of the centroid of the entire region. I'm going to use the base as my reference line. Just to write it down one more time. we have summation of y bar I, a sub I divided by the total area, summation of each individual area. And I'm going to kind of draw this dashed line in right here. My top rectangle has its own centroid, and the bottom rectangle has its own centroid at those positions. The composite centroid is probably going to be somewhere in between these, somewhere around maybe this location. Don't know exactly where that is until I do the calculation, but if we got way up here or way down there, it wouldn't be right. It's a good idea to kind of pencil in where you think it might be. All right, so the distance from the centroid, distance from the reference line to the centroid of the top piece is going to be 5.5 centimeters. It takes 5 centimeters to get to the edge, and then another ½ centimeter to get to the centroid of piece number 1. So the y bar is going to be 5.5. The area of piece number 1 is 1 by 5. For piece number 2, it's going to be this stem location from the reference line to its centroid. It's going to be 2.5. All right, so we're going to have 2.5 times its area. It's 5 by 1. And we're going to divide that by the total area, 1 by 5 plus 5 by 1. Let's see what we get for that. Yeah, I got exactly 4 centimeters from the reference line to the centroid of the entire section. Right. Next, we're going to find our moment of inertia. And just to write it down again, moment of inertia of the cross-section about its entire composite centroid is going to be the summation of each section's own moment of inertia about its own centroid plus the AD squared term, where the A is the area of each piece, and the D is the distance between that piece's centroid and the centroid of the entire cross-section. In this case, we have 2 pieces, so we're going to do the summation from 1 to 2. All right, for the top one, the I is 1/12, the base times the height cubed plus its area times 5.5 minus 4 squared. Okay, so this distance is 5.5. Distance from the reference line is 4. So the distance is going to be 5.5 minus 4. It's the distance between those axes. For the bottom piece, piece number 2, moment of inertia is 1/12, the base times the height cubed. Now this time it's the 5 that's cubed, plus the area times the distance between this centroid and the entire cross-section centroid squared. So in this case, it's going to be 4 minus 2.5, that quantity squared. All right, let's calculate these numbers. And when I calculate them out, I ended up with 33.3 centimeters to the 4th power. All right, so those are some examples of finding the centroid and finding the moment of inertia about the horizontal axis that goes through the centroid. And again, just to give you a heads up on why we're going to do this, why we've done this, so we're going to end up using the moment of inertia about the centroid in our formulas for calculating beam stresses.